Thanks for that kind intro. So as Joshua mentioned, I'm going to talk a little bit about software as hardware, and an amazing point in time when you could use that to actually fly to the moon. And a little bit about software and hardware. Nowadays we tend to think about it as a physical distinction. Hardware is your computer, it's the parts you can see and touch. Software are the instructions for that hardware, and it's stored somewhere in there, but it's not something you tend to really see. That wasn't always the case. Likewise, software wasn't always as prestigious as it is now. It was seen initially as just part of making the software or the hardware. You write something to make it go, but wasn't seen as like a separate practice. One of the many legacies of the Apollo space missions was changing that. Margaret Hamilton was the one to coin the term software engineering, and a lot of software engineering practices were formalized at that time. It was a lot more recognized as actually a hard thing to do and something that needs a lot of thought. And so you may be familiar with the picture on the left. This is Margaret Hamilton with a printout of code for the Apollo 11 mission. And I think there might be another mission in there a little bit somewhere. And on the right is a woman demonstrating what that code turned into. Computers can't read telephone books worth of code, so they had to use a different form. And on the right is the module holding that software, the core root memory module, which I'll talk about a little more in a bit. Well, right now, actually. So there's two types of memory that were used in the Apollo program. There's core memory, which is fascinating, but I won't talk about it much. And this is the erasable memory, so they could read and write to this memory on the left. On the right is core rote memory, and this memory was read-only, and it's made out of these hair-thin copper wires, and it was threaded through, or intentionally not threaded through, iron cores. And that's the red rings that you see there in the middle. So the way that this core root memory worked, the wires would either go through the core and the computer would read that as a 1, or it'd go around the core and the computer would read that as a 0. And then there were also wires that went through the cores to help the computer find the core's location. So as the computer was going to each core to read the software, it would check to see if it was a 0 or a 1. And if you look, I'm going to use this laser pointer. Okay, great. So on the right, these are all zeros, because they're not going through a core. And then in the middle here, these are either 1s or wires to help find the core. The other amazing thing about core root memory is that it was all hand-woven. And it was all hand-woven by women. They worked for the Raytheon Company in Waltham, Massachusetts, and a lot of them were former watchmakers for the Waltham Watch Co. And some were also said to be seamstresses as well. And you may be wondering, could handmade memory be any good? The answer is, it was very good. The design was excellent in that the distinction between a 0 and a 1 was physical, which means that it was pretty hard to destroy. During the Apollo 12 mission, a shuttle was actually struck by lightning during launch, and they had to reboot the computer. Of course, all the information in the erasable memory was lost, but the software was still intact, so they were able to pick up without any issues, which undoubtedly saved a lot of astronauts' lives. In terms of the execution of the actual weaving itself, that was also excellent. We don't have a lot of first-hand accounts of what it was like to actually weave this memory, but managers of the core root memory weavers had nothing but praise for their work. They talked about how seriously they took their work and the direct connection they made between the astronauts' lives and bringing them home safely and the care they took with actually weaving the memory. This was also proven in the mid-60s when Raytheon had a strike. The workers weren't making core root memory, but their managers tried to keep the project on track, so they tried their hand at making core root memory. It was all scrap. They couldn't use any of it. They didn't have the expertise and care and skill that these women had acquired. There's some other reasons why I'm really excited and fascinated about core root memory. It's very unique in time, and I think kind of sits at the confluence of a lot of technological and social forces in the United States. It was a bridge between vacuum tube computers and integrated chip computers, or computer chips that we're more familiar with today, which is really cool. It was really only used on the Apollo space missions because it was so expensive and time intensive to make. It was pretty quickly replaced with computer chips. The other aspect of it that's pretty cool is that it's one of the few times that electronics were manufactured in the same place that they were actually designed. So the software was written at MIT in Cambridge, Massachusetts, and then transported like 12 miles to Waltham and hard-coded there. So there's this really cool cottage industry of advanced electronics. Likewise, coming at the end of like watchmaking and seamstress and clothing manufacturing is pretty cool, because imagine working on watches and then working on space shuttles. It's kind of this amazing transition between old school industrial practices and advanced space technology. So if you're as excited about core root memory as I am, I put together now a how-to guide. Step 1, load the component with magnetic iron cores. Step 2, weave the software into the component. They used hollow needles filled with about 20 feet of copper wire and threaded that through the cores based on what the software required. And these two women are working together. But I've seen a lot of footage and photos of women working solo as well with just this machine. And the only part of this process that they really managed to automate is moving the machine to the next correct core to weave. And also this machine helped kind of push the wire around those nylon pins, the white pins there, to keep it neat and tidy, but that was it as far as automation. So once you thread the needle through the iron core, the machine will move you to the next spot. And then finally, to finish the module, you solder the wire in place. Once you finish weaving, remove the nylon pins, press it down to flatten the wires, and then fold those wires into the module itself. So as you can see, it's a pretty tactile experience actually making this hardware. Give it a good final pat. And then finally, run electrical tests. They used another version of the software on paper tape to run electrical tests on the module, make sure it was working as expected, and then pot the module. Potting electronics is a term I really like, thanks to the domestic food preservation connotations it has, but basically they covered the module in plastic to protect it from the elements and protect it during launch. One aspect of this research project that hasn't been as exciting is that there aren't any direct references or direct quotes really, or recording of these women's experiences of what it's like to make core root memory. I would love to talk to them, especially because I'm currently based in the Boston area, so if anyone has thoughts on how to get in touch with people that either wove core root memory, or their family members, if they talked about what that experience is like, I'd love to preserve their memories as well. These are names that I've managed to find so far. So yeah, get in touch if you have any thoughts on that. Likewise, thinking about what these women's experiences were like and not really having any insight into that has made me think about what it's like for workers in electronics manufacturing today. There isn't a lot of transparency in their working conditions. In a lot of ways, it feels like a step backwards, and they don't have much of a voice either. So yeah, something to think about in terms of how American companies continue to manufacture electronics and the status they give their workers. So that's my talk. Thanks for listening.